Hello everyone. Today we will see how to use the built-in LEDs provided in the Sync Ultra Scale Plus board, especially in the ZCU102 board. So I'm going to control the LEDs available in my development board using my uh, SoC. I'm going to create a new project. I'm going to select the project location. Say this is LED control. I'm saving my project in one subdirectory. Select your board. Mine is ZCU102. Finish. So coming to this project, again there is no custom Verilog modules I am creating here. I'm directly going into the block design. So I will create a block design. I'm adding an IP. So first IP is my sync. Run block automation. So the board presets will be applied. And in that here I have two axis ports. I need only one. I'm going to control only the LED. This is the interrupt thing. You can remove that also. I'm not using any interrupts here. L to PS, I'm not using any interrupt. That's it. Okay. So let's see about this thing. This is M. M is for master. So M AXI. So AXI is the protocol that we are going to use to communicate. HP is a high performance, stands for high performance. Now let me include my LEDs. So in order to include my LED, what you want to communicate or what the processor has to communicate with is an IP called GPIO, general purpose IO, input output. So I'll show you that IP first. You search GPIO here, you'll get the IP. So this is your IP. I'll maximize it. So you can see that in your IP, you have a slave pin. So this master pin will be connected to the slave. So that will be done with the run connection automation, or you can do it manually also. So this is what is going to happen. And the clock, the PL clock will be connected to this clock, and reset will also be connected. And for this clock, this is the clock for your AXI. So this clock will be connected to AXI also. All those things will happen all of a sudden with run connection automation. I will explain you just before doing that. If you look at this AXI GPIO, your LEDs, my target is to connect the LEDs to the SoC. So LED is actually an IO device and it should be connected to this SoC. So for the SoC, here actually we are using the concept of memory mapped IO. So this will be a memory address. These LEDs will be just a memory address for your SoC. So GPIO will have some memory address and the SoC will be communicating to the GPIO. He will be simply transferring data to that particular memory address. And we should ensure that this GPIO is connected to the LED. Here you can do it like this. Instead of custom, you can select here your LED 8-bit option is there. So this board has got switches, 8-bit dip switches are there, and 5-bit push button switches are also there. So when you are using it for or reading some input from the switch, you have to select this. Now right now I am going to connect my or control my LEDs from the PS. So I am connecting LED. Now why you require custom? Sometimes you will be transferring data to some custom pins of your particular module. You will have some RTL modules, Verilog modules, or some IP. You can ultimately convert it to some IP, and to which you are sending data to the pins. But here I am connecting the GPIO. The purpose is to send data to the LED. So it's an 8-bit pin. So in the IP configuration, you can change the bit width also. Since it is LED, it is fixed to 8 because in the board it is by default you are having an 8-bit LED. Now click OK. I will go for run connection automation. You select all, click OK. So as I mentioned earlier, you can see that all connections are done. Apart from these two, you can see some other blocks are also added. One is for processor reset system, because the processor reset is directly going to this, and from the system it's going for all the peripheral device. Okay, and you can see the clock has been already connected to this particular GPIO, this reset system, and this AXI port, and obviously to another thing called AXI interconnect, which also automatically appeared. I have not connected that manually. The tool will automatically assign that. The purpose is that in order to send data from this master to the slave, you need to transfer it from master to slave. There you need an AXI interconnect. So from this master to slave of your AXI interconnect it comes, then from the master of AXI interconnect to the another slave. Usually sometimes you may have another GPIO pin also. At that time you need to you will have some other AXI GPIO pins in this AXI interconnect. So after completing this, the next step is to validate the design. So validation is successful. So once the validation is successful, the next step is to generate the Verilog code. Now you have only the, if you look at the design sources, you have only the BD file, that is the block design. Right click and create HDL wrapper. So with that your Verilog file will be generated. After that you can go for, now you can see that the wrapper file is created, .v file is generated. If you open that, you can see the Verilog code. So this is the beauty of block design. You don't want to code it from scratch. You can directly start with this block design. Now you can go for bitstream generation. So once the bitstream is generated, you can export this hardware and move on to Vitis for further coding. So we will skip this section. We are actually done with the implementation or bitstream generation. Now I'm not interested in any reports. I'm just cancelling that. So the bitstream is generated. Now you can export your hardware. So file, export hardware. Next, you should include your bitstream. So I'm programming from the Vitis environment. That's why I have to include this bitstream, which is actually the machine language for your FPGA or the PL part. So we have the PS and the PL part. So this is the machine language file for your FPGA or the PL. So I'm storing it in the same folder. That's my project work folder. So I have exported the complete block design to that project folder. Now I can launch Vitis. So in order to arrange the things properly, so in my project folder, so this was my project folder, you can see that the hardware wrapper file has been created, .xsf file has been created. For the Vitis, I'm going to keep a subfolder in this, so Vitis code or Vitis application, you can say. So this will be my directory for Vitis. So here I have Zinc tutorials. Where is it? Yeah, Zinc tutorials. LED control was my Verilog or Vivada project, and in Vitis code I am saving the Vitis part. So create application project. Next, you have to select your own custom source. Okay, you have to click on this browse. So you have to select your custom hardware. My hardware was saved here. Okay, this is the custom block design that I have created. Click on next. Here this particular SoC has two Cortex A53 and Cortex R5. So this is actually a quad core and this is a dual core Cortex. I'm using the first core of this quad core processor. You can give any name for your application. I'm just giving app. That's it. Click next. I'm going to create an MDC application, finish. So previously we used the default hello world code. Now I'm going to use my own custom code. So that's why I have selected the MDC application, not C++, but C. So this is your Vitis environment. Now here you can see your source codes. There is no source codes here because I have opened an empty application. Here new file, you can create your own custom source code. So this is my LED source code .c. You should give .c. Finish. So I have already done some code here. So here you can see xparameter.h. I have included a header file xparameter.h. If you open this xparameter, it comes actually with your custom hardware, where if you find GPIO, you can see there is one instance. There is one instance for this GPIO. So this is your particular GPIO. You have one GPIO to communicate with the LEDs. So this is the actual memory address or the base address of your GPIO. What the processor PS has to do is simply transfer the data, an 8-bit data, to this address. You can see the LED will be glowing accordingly. So this is the base address of your GPIO. So that is connected to the LED. So we can use this parameter. It will become, it makes more readable. Rather than including this data, you can just use this name. So I'm just copying this name, or it's already done. Here you can see that xpar GPIO 0 base address. You can use the same thing. I'm just passing 0f to that address, so it will come to that GPIO and ultimately to the LED. So this is the function for sending data. I'm sending an 8-bit data. You can use _out 8-bit. So I'm passing 0f first. 0f means it's in hex, so you'll have 4 zeros and 4 ones, right? So 4 LEDs will be off and 4 LEDs will be on, and a delay of 3 seconds. This is for a delay of 3 seconds. You can use sleep of 3 also. I'm using usually micro sleep of 3 into 10 raised to 6. Right? You can use like this also, sleep of 3. Okay, manage the header accordingly. And this is just for troubleshooting purpose, whether it's working properly or I'm just printing in. It's printf, so I'm printing in the serial monitor. Let me open the serial monitor also. In the show view, type serial monitor with the serial terminal will come there. I'm keeping my board powered on. Okay, so here the serial terminal, my board is connected to COM7. You can identify it from the device manager. So this is the port where your UART wire is connected, UART, not the JTAG, UART. Okay, because this communication will be from the board through UART. You are seeing it in the terminal. Okay, so once you have done coding, you just build the project. So building is going on. Once build is completed, you can just run your code, run your configuration. Then you can see the corresponding output in the board. You can see the terminal. Along with that, you can see the result in the board also. Okay, build has been finished. It's about to finish. Once the build is finished, you can see in the project folder. If you look at this was my project folder where I have the Vitis code. So if you look at the app, here you will have the debug file. So where you can see app.elf, elf is executable and linkable format. This is your machine language file that has to be dumped into your So build has been finished. So go for run configurations, where you have to select this one, single application debug. So your configuration will pop up. You can directly go for run, or you can just verify all those things once. Standalone application in the main, go to application, say your same Cortex has been selected. You can see here your file is app.elf, that's already loaded. And if you look at the target, program FPG is being ticked. Sometimes you will uncheck it because you will be can program it from the Vivado also. You will give some control signals from here and you will code the PL from the Vivado. But here I am coding the PL also, the FPGA program. That is the bit stream that we have exported from Vivado. That is also being dumped. So that's why I have ticked it, program FPGA also. Then click on run. Serial terminal. you can see sending 0F and F0. So it's done. That's it. So if you look at the board, you can see that these LEDs are actually off right now. I'm going to program the FPGA. So here the programming FPGA is going on. Once it is completed, you can see over here. So we expect a 0 0 0 1 1 1 1, that is 0F initially. Yeah, you can see 4 LEDs are off. After 3 seconds, first 4 LEDs are on and the remaining 4 LEDs are off. That's it.